Good afternoon, everybody. Thank you for coming to the last session, or second to last session of the day. I'm N.Dupont, as Brand said, working on Cyborg, and really excited to talk to you guys about what we believe is the final missing piece to making enterprise AI as a whole a reality, which is solving the privacy and confidentiality and security problem via encrypted vector databases. So in this session, we'll be talking about kind of what's holding up AI deployments in the enterprise, what the missing piece is for security to be able to make it a reality, how we can secure it with encrypted vector databases, and how you can bring it to production today. Firstly, I'll start by setting the field, which is that AI is everywhere today, except in production. You might have seen the MIT paper making the rounds over the summer saying that 95% of Gen AI pilots are failing to transition from POC to production, and security is one of the primary factors in that. And so companies are asking to see ROI for their massive AI investments, and they're having trouble doing that because of security and data privacy. Enterprise AI requires proprietary data. That's a key requirement for it to generate real value and generate that ROI for those enterprises from their massive AI investments. But there's a huge security gap that's preventing that, or that creates unmitigated risk if brought to production. To explain that, I've got a few visuals. This is a grossly oversimplified view of what the enterprise looked like before AI. Traditionally, data was siloed in an organization across different parts, corporate IP, customer records, CRM, engineering, finance, etc. And while this was a nightmare for CIOs that wanted to organize that data and make it available throughout the organization, it wasn't all that bad from a security perspective. The reason being, as an attacker who wants to get a cross-section of the organization's data, I have to breach each one of these silos. I have to go through the security landscape for each one of these. Audit trails, I'm much more likely to get caught up at some point. There's a lot more friction, which works in the favor of the defenders, typically. Now, with AI, we're seeing a huge paradigm shift. Enterprise data is becoming centralized. All of these disparate silos are getting centralized into typically a vector store, a vector database, that is then able to act as the knowledge base and the memory for a large language model, whether it be for a RAG application or for an agentic workflow. And that creates a huge security risk. You're centralizing all this data, which reduces the attack surface, but it makes the blast radius significantly larger. Now, an attacker only needs to focus on a single point, the vector store, to be able to get a cross-section of the organization's entire data. And further, vector databases are comically ill-equipped to deal with this type of security risk. Instead of explaining to you what that risk is, I'll just show you guys. So here I have a Jupyter notebook that is going to show an attack exploit on a very popular vector database called Quadrant. We have similar exploits on our GitHub on Chroma and other vector databases. And here we'll take sensitive text, synthetic data, embed it, store into Quadrant, then we'll extract it from its lack of security around the embeddings via side channel attack, and then further we'll take those vector embeddings and invert them back to the original text. So we'll run it cell by cell here. We're using the OpenAI embedding model, text embedding ATA 002, and then we're using something called vec2text, which is a corrector model that we can use to be able to invert vector embeddings back into the original modality that's specifically trained for the OpenAI embedding model. Then we'll launch Quadrant in Docker as a sub-process. And with the memory map storage right here, we'll create a collection to be able to store the embeddings, store the data. And we've got some fake sensitive documents here. My social security number is 818, blah, 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 password, medical diagnoses, personal information. Go ahead and create those. And we'll generate embeddings using the OpenAI embedding model, and then store them inside of Quadrant using their Python client. So we'll generate those, and we've got 6 vector embeddings, one for each one of these texts that are stored in the vector database. So this is all very standard so far, the way that you would ingest data, obviously on a much larger scale in production for AI applications. Now we'll do that first part that I mentioned, the side channel attack, which is reading the memory mapped. So doing essentially a memory dump of Quadrant to be able to access the vector embeddings that are stored within it using the memory map files. This is one of many attack vectors. These vector databases, and I don't mean to pick on Quadrant specifically, but basically all of them have little to no encryption, and they delegate it to the OS. So if you have access, any type of privileged access, you can get the data. If the API key is the only factor of security, so you can also attack it that way. But this is one of the side channel attacks. So we'll run this cell here, and we will scan. We scan the memory map file, and we find these 6 vectors by looking for a pattern of 1,536 floating point values in a row that are stored, which are these vector embeddings. And then now we've got these vector embeddings extracted that are the dense representation of those texts, not the texts themselves, and we can now invert them. So we'll run this cell here that runs vec2text. We put them in a PyTorch tensor, and then use vec2text to be able to invert the embeddings. It's configurable. Here we're using 4 steps. The more steps you do, the higher the quality of the reproduced outcome. And then we also use a beam search algorithm to be able to reorder the original grammar. So we'll run that, and this is running entirely locally. So this is the original text that we were trying to reproduce from the embedding. And as you can see, we're able to reproduce with 96% accuracy my social security number without the perfect match, but close enough for an attacker to reduce their search. Now, the next one, password for admin account is secure pass 123, we get a perfect match. Patient diagnosed with type 2 diabetes, prescribed metformin, we get a perfect match, so on and so forth. So this is a huge risk. We haven't seen it in production be exploited yet as far as we know publicly, but it's only a matter of time. You can extract these vector embeddings, and they are not one-way hashes. They are just representations of the original data, and we can invert them back to the original data. So what do we see? We saw that vector embeddings can be inverted back to original data. This is not just text, also image embeddings. So there's a company called Iron Core Labs that did a nice demo of this with face scans. They can be inverted back to the original data. Because of that, they should be protected with the level of protection that you would use for that source data, and not just treated like they are ciphertext. And standard vector databases have little to no security against leaking these embeddings in plain text, and therefore allowing attackers to invert them. So what would a solution look like? How do you solve this, and how do you address this vector database gap? First thing, you need to have cryptographic protections in order to prevent the embedding leakage in the first place. So whatever is leaked, both via this side channel attack, but as well via logs and unauthorized access, is in ciphertext form. It must be compatible with existing frameworks and simple to implement, because as most of us know, if you have to compromise either functionality or security, unfortunately, usually security is the thing that gets compromised. And lastly, it must maintain high performance. These enterprise AI applications are dealing with tens of thousands of queries per second, tens, hundreds, oftentimes billions of vector embeddings, and the solution needs to scale to the performance needs of those applications. And we have a demo for what one proposed solution to this looks like, and then we'll explain how it works. So here's the same notebook, essentially, that is using CyborgDB. So CyborgDB is our encrypted vector proxy that adds those solutions, those cryptographic solutions, between an AI application and a backing store like Postgres, Redis, S3, so on and so forth. In this case, in this demo, we'll be using Postgres. So we'll do the initial setup as well, create the OpenAI client, and load the corrector model for vector text for the OpenAI embedding model. I'll take a second. And then we'll set up CyborgDB. So as I mentioned, this demo is using Postgres. So we set our connection string here. Forgive my Postgres password being password. I swear this is not what I use in production. And we set up our CyborgDB client with a DB config connecting to Postgres and create an index. And here is one of the important parts is we pass in an index key. We have integrations with key management services, and we'll get into that when we get to diagrams. But the cryptography with CyborgDB is explicit, meaning that each index, which is virtual, has an encryption key, and that is used as the master key to derive all the other keys to encrypt absolutely everything within the index. Here, it's just from an environment variable so that we can replicate it in future runs. So we'll go ahead. We created the encrypted index, and we've got the same sensitive documents that I showed you in the quadrant demo. And now we'll generate the embeddings same way with get embeddings OpenAI, and we upsert the embeddings as with the ID, the vector embedding, and the original contents. And all of this all the cryptography is transparent to the developer. So this upsert call performs the encryption and the indexing of that. So we have those 6 embeddings. They're now stored in CyborgDB. And now we'll try to do a similar side channel attack on CyborgDB by connecting directly to the Postgres client, to the Postgres backend that's storing it, dumping the embeddings from that, and trying to use those embeddings to invert them back to the original text. So we will run this. And we extracted 6 encrypted embeddings. The reason why we know they're encrypted is we just compute the entropy of the embedding and check, is this in floating point format? If not, we assume it's encrypted, but we'll still try to invert them. And you see the first extracted embedding here. Usually, vector embeddings are they're a list of floating points that are all relatively close in value. And here we have, huge 10 to the 33rd, 10 to the minus 20. So we can tell that it's not in the original format that it desires. And then we'll run the inversion script in the exact same way. And so for the original text here, for that vector embedding, which again was encrypted, vector text is going to try to converge by running through the gradient backwards and backpropagating the model, try to converge on an original text. As you can see, it keeps saying set element 0 to a random sequence. This is because it's unable to converge because it's ciphertext. And it's not able to reconstruct anything, so the similarity is 0. And not to spoil it for you guys, but this will be the same for all of the examples here because the embeddings are encrypted. So this solution demo, both the VectorDB inversion demo that I showed on Quadrant, but also we have it on ChromaDB and others, as well as the demo running with CyborgDB, is available on our GitHub, cyborginc/vectordb-inversion-demo for you guys to try it out. Don't just take my word for it. So what we showed you was CyborgDB. It is a drop-in vector proxy that adds in end-to-end encryption throughout the inference lifecycle. So from the time that the vector embeddings are upserted into CyborgDB to the time that they are queried and retrieved back to the developer. Those are the 2 endpoints, and it's encrypted throughout that process between both those endpoints. We have a drop-in API. As you saw, it's a very similar workflow to what we were doing with Quadrant. The only difference is that encryption keys are explicit and involved in the first place, so that you're able to do a drop-in replacement in minutes, not days, and use your existing infrastructure. You're using Postgres, you can use Postgres. And it is high performance. We didn't show that here, but we have a great technical partnership with NVIDIA, which we've published some joint work we've done to be able to minimize the cryptographic overhead of CyborgDB, as well as have a GPU accelerated mode meant for those billion vector scale operations. I've got a few diagrams for you guys. So this is a really high-level overview of a RAG application. If you're not familiar, RAG, Retrieval Augmented Generation, is the most common paradigm for enterprise and generally AI applications as a whole. It is where you're trying to augment the model knowledge with information that was not available to the model at training. So this might be newer information since the training, or more relevant, private information to you or to your company, to your organization, that the LLM couldn't have in the first place. And because LLMs have limited context windows and need to be focused, you can't just feed in your entire knowledge base into it. You need to intelligently select context that is relevant for the query or for the action of the agent, and feed that in as context to the LLM in order for it to be able to give you an answer or take an action that is desirable and rooted in your proprietary information. So the way that it works, you start with confidential data, feed it to an embedding model. In the example here, we were using the OpenAI text ADA embedding model. Those vector embeddings are then fed to CyborgDB, where the cryptography is happening. Those vector embeddings and the index are then stored in an encrypted backing store, which is used for ingestion as well as for querying, where a query can come in, CyborgDB can retrieve the relevant chunks, decrypt them, and feed them to the LLM. So that both at rest and in use, the data sitting within the backing store, the knowledge base itself, remains encrypted. That's fed with a system prompt to the LLM, and a confidential answer is generated. Let's zoom into what the ingestion pipeline looks like for this. This is the most common way that we've done it with our customers. You start with confidential data. You have a parsing pipeline that will take that data. If it's PDFs, you might have PDF parsing to be able to get the original text, to extract the images. You then have chunking. If you have a 1,000-page PDF, the information that is relevant to the query or to the action that the agent is trying to take might not need all 1,000 pages. So chunking allows you to reduce that upfront and have page-based chunking or context-based chunking. Those chunks are then fed to the embedding model to be able to transform the text or the images or the audio, whatever the original modality is, into vector embeddings. And they're also fed to CyborgDB. So the vector embeddings in the original data is fed to CyborgDB. We interface with your key management service in order to be able to perform the encryption with your keys. And then the resulting tokens and ciphertext are stored in the backing store, Postgres, Redis, Mongo, etc. At query time, it's a similar process where the query is embedded. The vector embedding from the query is then fed to CyborgDB, but we also support metadata filtering. So you're able to do, using the MongoDB query expression and projection language, you can feed in JSON via your query, and that comes into CyborgDB for metadata pre and post filtering. It will use the key from the key management service and connect to the backing store to be able to retrieve the top K chunks that are relevant, decrypt just those, and feed them to the LLM alongside the system prompt and the user prompt or query to be able to then generate a confidential answer and do this at a low latency cost. So zooming into what's happening inside of CyborgDB, where the cryptography is happening. As I mentioned, we take in vector embeddings, and we take in metadata and contents. These are items. This is the structure of the items that we take in. The vector embeddings, the IDs, which are strings for the ID for that item. The metadata, which is optional. It's a JSON dictionary. And the contents in bytes, so the original data or the original chunk. The metadata and the contents, pretty simply, are encrypted using AES-256 in GCM mode, authenticated encryption that's powered by OpenSSL, the libcrypto, and that's stored in the encrypted backing store. We also have a step for metadata pre-filtering and clustering that we don't highlight here. But the important part, this part is very easy, and you can roll that yourself. The important part is how do you enable the similarity search to be able to find the most relevant vector embeddings for the query without decryption. How do you do it over ciphertext? So we take the vector embeddings, we feed them to a k-means clustering model that is trained on the data that's automatically done by CyborgDB and retrained as the data set grows or changes in distribution. And that k-means clustering assigns each embedding to a cluster. We also have quantization that's available to be able to compress the vector embeddings to save space. And then that's fed to our encrypted indexing engine that then stores the encrypted tokens in the encrypted index store. I won't leave it at that because that's a bit of a black box for you guys. So let's zoom into the encrypted indexing, what's happening. So we start with those k-means centroid lists. So we have for each vector embedding, which centroid or centroids it is clustered into. That gives us a unique ID for that embedding and the centroid combination. And then we create a centroid seed for each one of those clusters. There's one per cluster and per index. And we compute an HMAC using the centroid ID and the key from the key management service. This can be done once at index creation or at index loading to be able to amortize the cost of this because it doesn't change per centroid. And that gives us essentially the base seed, the key that is used to index the rest for all the embeddings within that centroid. So then taking that seed, we take the seed and we also have a counter map that counts the number of items, number of vectors that are stored in each one of those centroids, in each one of those clusters. We take the counter map, we get a counter for how many are currently in the cluster for this vector embedding. And post increment the counter, and then we compute. We have a binary tree that's where the permutation function is SHA-3, and we compute two hashes off of that, the seed and the counter, a left hash and a right hash. The left hash is used as the token that will represent this specific embedding within the encrypted backing store. And the right hash is used as the key, the 256-bit encryption key, to actually encrypt the embedding itself. So each embedding has its own encryption key that is derived from the original key and the counter. This creates a binary tree where this creates a list of nodes, which we can then compute back on the fly. We can do this process again by selecting a centroid that we want to search through and regenerate all of the nodes to be able to retrieve them from the backing store and regenerate the keys on the fly to be able to decrypt the embeddings and do and feed them back for the final similarity search, or feed them back to return the top K results to the query. And so it's a forward private indexing scheme that guarantees that on the database side, you can't tell which embeddings are related and can't tell the similarity between those while still being able to do the similarity search. In terms of performance, this is a graph from our work that we did with NVIDIA, where we did some GPU acceleration work. So you've got a logarithmic scale on the left here of queries per second for retrieval, and on the x-axis is the recall, converging at 100% recall. The blue line is our CPU version of CyborgDB, and the faint blue line is without the cryptography. So running it without any of the cryptographic overhead induced by the HMAC, the SHA-3, and the AES-256 encryption and decryption. So at low recalls, we have about a 15% overhead. Again, this is a logarithmic scale, 15 to 20% overhead. And at high recalls, which is what really matters in most applications, you have a single-digit percentage cost. The reason for that is that we're spending more time on centroid selection, on fine search, on re-ranking, that amortize the cost of the cryptography, which is linear. And the green line, same story, GPU acceleration, plaintext versus ciphertext. The bigger gap here is because the HMAC needs to be computed on CPU. The binary tree can be computed on GPU, but the cost there and the incremental cost of those transfers between CPU and GPU cause the cryptography to have a bigger gap. But we still, comparing ciphertext to ciphertext, we get a 7x performance uplift running on GPU for query. And about a 1% build time overhead with the cryptography between CyborgDB unencrypted and encrypted. So this is when you're adding vectors to the index. So we have a table here to compare various implementations of secure encrypted vector search. Starting at the top is our plaintext database. This is essentially every vector database out there today. Pinecone, Chroma, Quadrant, Weaviate, Milvus, so on and so forth. So no encryption or delegated to disk or encryption at rest at best. Performance is fast. Obviously, it's this is the baseline table stakes highest performance solution. The deployment, it's very easy to deploy. Docker image, Kubernetes, there is no overhead with key management or anything, but you're leaking data like I showed in the example notebook earlier. Using homomorphic encryption or secure multi-party compute, there is some interesting work in academia using fourth generation fully homomorphic encryption like CKKS that allows you to do approximate arithmetic to be able to do the vector search. Strong cryptography from what's shown in the field so far. However, the main problem is performance. You've got several orders of magnitude. It's about 1,000x slower than a plaintext implementation. It's hard to integrate as a result, and just far from production for now, similar to it's fully homomorphic seems to always be a few years away. TE only, this is using a trusted execution environment, confidential computing, think AMD SEV-SNP, Intel TDX or Intel SGX, and running a standard vector database within the trusted execution environment. The security guarantees are relatively strong. There's a caveat here that I had to add last week, which is that recent exploits have shown that trusted execution environments are vulnerable to physical compromise using a memory interposer on the RAM DIMMs. So big asterisk there. Performance is fast. It uses deterministic encryption, so it's a flat cost throughout. However, the deployment is quite complex because you need to handle attestation on top of the encryption. So it's a largely incomplete solution with some big gaps in security today. And then lastly, the category that we've shown you here, which is a confidential vector database, where the encryption is layered in at the application layer within the vector database. So this is strong security guarantees, again, using cryptographic primitives that are well established, AES-256, HMAC, and SHA-3. Fast performance, like we saw. It's an easy to deploy solution, and it's production grade today and already in production with a number of our customers. So CyborgDB is available today. It's available we have a very generous free tier for anybody that wants to evaluate it, and also a nice startup and nonprofit program. You are able to go try it out, validate this, and tell us if you find an exploit. We'd be happy to improve it as a result. Available on Docker Hub, PyPy for pip install, TypeScript, JavaScript via NPM, and on the Go package repository. And to wrap up, I firmly believe that secure AI is the missing piece to be able to make enterprise AI reality, which is going to define the next decade of the enterprise. And the secure or confidential vector database is the piece we need to be able to make it happen. So with that, I'll pause for any questions. And this QR code brings you to our site and docs where we dive into a lot more detail about our implementation.
It's awesome.
Yeah, first of all, thank you. That was a great presentation. When you say GPU encryption, do you use OpenSSL for that part also?
No. So the encryption in the sense of AES and the HMAC instruction is all done on CPU, largely because there are no formally verified schemes running on GPU that we know of today. And also because GPUs are vulnerable to some side channel attacks like timing attacks that CPU implementations deal with much better. The part that we're doing on GPU is the permutation of the SHA-3 of the tree, the binary tree using SHA-3. That's not involving any secrets, so it's not the side channel attack is not a concern. And it's there are no interdependencies other than the counters, so we can pre-compute the counters and the HMAC seeds on the CPU, send that, memcopy that over to the GPU, and then we have our own catch-hack implementation on GPU that is hand optimized for these fixed width operations, where we're able to then generate, on say 40,000 threads on the GPU, we can generate 40,000 nodes in one operation as opposed to the sequential operation on CPU.
Thank you. And do you think that the cryptographic operation and encryption workload, will it be shifted to GPU? Because nowadays most of the workload is for GPU only, but when there is a lot of data and the things that you're doing, then you also need a very high-end CPU for the encryption. Then we are dividing, we need a very high-end CPU and a high-end GPU. If the overall workload is for GPU, why not do the cryptographic operation on GPU only?
That's a good point. I would say from our experience in the working on AI and machine learning applications, most of, when you say the GPU, the workload is on the GPU, most of the cost there is not actually the data that you're feeding into the model, it's the model itself, right? So it's a memory-bound operation. You're doing a lot of memory-bound, and then the CPU, the compute-bound is the matrix multiplication, and you're streaming essentially every layer of the large language model for every token recursively. And so if you're not doing cryptography on the model itself, which is not what we're talking about here, there is some work there, you're only doing the cryptography on the context that you're feeding into the context window of the GPU, of the model into the GPU. So actually the cost of cryptography on CPU is not the bottleneck, even in these operations. Now, if you were trying to encrypt the entire model and run that confidentially, I think that would be a very different story.
Thank you.
So I have a question that when you want to query something and should you, and is the data actually decrypted? Yes.
When you from the developer lens or within the database?
From the database.
From the database, no. So there's two parts to the search. So there's the core search and the fine search. The core search is where we select the centroid and select the nodes that we want to retrieve back from the database. All of that, nothing is in plain text. There's a variable, there's a parameter in there that's called the top K that you want to retrieve. You want to find the top 100 closest results. We can retrieve back the nodes from the centroids with the right inverted index. We can retrieve back just those nodes. And then to be able to re-rank within the top 100, we then decrypt it and do your Euclidean, squared Euclidean, cosine search on the vectors and return that back to the client. So there is still, to the developer, it's all in plain text. And there is some plain text decryption, but it's only for the top K that you're retrieving. So on 1 billion vectors, retrieving back the top 100, it's a much smaller subset of the data set that is decrypted at the last part of the query.
Okay, thank you.
Sure.
Yeah, thank you. That was one of the best presentations in terms of what I was able to understand. Yeah, during those 3 days, maybe because I'm not so confident in the cryptography, but I just really quickly Googled, and if you'd be so kind to get back to your prior slide, eventually comparison of different storages. Yeah, exactly.
Yes.
I'm curious at the very first cell where you have no encryption, right? And on prior slides, you had such database engines like Mongo, Redis, and so on and so forth, right?
Sure.
So currently, really quickly, Mongo Atlas, at the end of June of this year, introduced, how it's called, queryable encryption, right? So, which seems to me doing pretty similar stuff,
Sure.
right? So I'm curious why you have a crossover there.
Yeah, so I probably should phrase that it's vector databases specifically that we're talking about, not standard databases, relational or document databases in the case of Mongo. I know that they released queryable encryption 3 years ago. Initially, Seni Camaro's team worked on that, and it was available for certain operations, equals, range queries. I'm not sure if this one has it for vector search specifically.
Seems to be, yes, yeah.
Then
It's like 2 months or 3 months old post. So it still seems to be beta, not a full release kind of production. But
and I should add an asterisk. Thank you for calling it out.
Yeah. Thank you. And also, just out of curiosity, right? So it's more kind of use case of extra encryption, right? Because normally, if those vector DBs will have an encryption out of the box at rest, you still may use it for really super sensitive data to have one more extra layer of encryption, because normally that's what you can do even now, right? To just encrypt particular fields in your table, right? Like with social security number, right? So to have extra protection, so maybe that will be another use case eventually for this service.
absolutely, the field level encryption is more for a structured database than a vector database, because the main challenge with a vector database very specifically is that you're not doing OLAP, OLTP queries. You're doing similarity search to be able to find the data that is most semantically relevant for your operation, and then you can do filtering on top of that. The field level encryption is applicable to the filtering, but not for the actual vector search itself. How do you ensure that which vectors can be decrypted or not and can be accessed is a problem that's not solvable via field level or row level encryption.
Okay, thank you.
Thanks. Thanks for an interesting talk. My question is about the very beginning. So before the encryption started, you were showing how you were in the demo extracting the plaintext out of the vector embeddings, and there were these small errors, right? You were seeing like it's not exactly the social security number, a few digits are wrong.
Yeah.
So if I would prompt the LLM and say, what is my social security number, would I get the same errors as well?
No, so great question. So I'll actually go back to this slide to show it, this query slide. So in a traditional RAG context, whether it's with Cyborg or with any other vector database, the vector embeddings are used to do the similarity search, and it returns back a list of IDs that are the most semantically relevant. Then there's a next step that is retrieving the original chunks with those IDs as the original text, and then feeding that to the LM. That's the original data. It can be stored separately. It can be stored within the vector database. In the case of Cyborg, we store it as well. And that's the original data. Now, encrypting that is very easy because it's just symmetric encryption. You can have role-based access control on that, so on and so forth. So you wouldn't have those errors feeding it into the LLM. This was a side channel actually targeting the vectors that are traditionally not used to feed anything to the LLM. There's something called refrag that Meta wrote a paper on, I think it was a few weeks ago, that does change this paradigm, but that's not used in production at all. So you wouldn't have those errors. This is just because we're using the vectors that are traditionally only used to do the similarity search, and then extracting the original information. And because they're not used, they don't contain the original information in a human intelligible sense, they're not secured as such. And that's kind of the point that we're trying to make.
Thank you.
Thank you very much. This sounds like proper revolution to me. I'm trying to understand, and this is really strangely good, I think. And
Thank you.
I couldn't fully understand yet, but I'm trying to. But two questions I would ask. One of them is you compete with trusted execution environments, TE-based solutions, and you're showing from the data owner's environment HSM and KMS like assistance, but it could have been TE assisted as well.
Sure.
Are you seeing TEs as like maybe broken, or why do you pose them as competing but not collaborating, assisting to your solution?
That's a really good point. And yeah, if you're using an HSM at KMS solution, it's using a secure enclave technology in some way, shape, or form, right? So it is within the same family of a TEE. In that comparison slide, it was specifically about running a vector database within a trusted execution environment and having that be the complete solution. With that said, our solution can use a TE for that key management service if you are using that as the root of trust. So it's definitely collaborating in that sense. What I mean to say is that the TEs themselves are not a complete solution. Even if you have a key management service as your TE, you can't do encrypted vector search on its own. Mm-hmm. You need both parts.
Okay. And I'm going to continue on TE side. So there is ARM CCA is coming, which is more of a complete solution because TE is at now 10 years of story, and ARM CCA promises a lot of high level of security. Would you reconsider that as well, like using, again, TEs? And if, let's say, the security of TEs were properly offered, not much side channel leakages, like how much of comparison there would be? And
sure.
Another quick attachment, like related question. With TE-based solutions, you could also offer model security in the data owner's environment, like vice versa. Did you explore from your approach any chance of sending the model into data owner's environment and providing any type of protection in a reverse manner? I have no idea how you guys manage, of course, but is there any technical possibility of that?
Yeah, so you bring up a lot of interesting points that we are actively researching and that we've done some work in. So firstly, in terms of considering the use of a TE, absolutely. I mean, we have, we're considering, we're planning to run a hosted version. This is all self-deployed in the, bring your own cloud type of application. But for customers that don't want to run the infrastructure themselves, having the TE as an additional way of ensuring that we don't have access to the data, in addition to CyborgDB itself, with a granular cryptography. So definitely something we consider in ARM-CC as well. In terms of would it compete if a TE was a complete solution? Only if it's, assuming the side channel thing you said that it's secured, but also the challenge with TEs is attestation, right? So if you have the data plane, which would be the vector database, within a trusted execution environment, within a confidential VM or whatnot, and you need to shard that database. Now you have multiple nodes that are each running in confidential computing, and they now need to attest each other to be able to validate, hey, this is a workload that is trusted, that is signed by the hardware, by AMD, by the ARM manufacturer, by Intel, so on and so forth. And now it becomes a much harder problem. Attestation point to point is already problematic today, and it's probably the hardest, the most complex thing to solve today in confidential computing. But if you're doing it between nodes in a sharded database, it's exponentially more difficult. Now, if both those things were solved, that would be great. We work with TEs because we also abstract away the data plane does not need to be in the TE, right? So the encrypted backing store can be outside of it, and then the proxy itself is stateless, can run in the TE. So maybe one day. And lastly, in terms of running the model within the TE, absolutely. We, as I mentioned, we have a technical partnership with NVIDIA. We've done work with NVIDIA Confidential Computing where the GPU memory is encrypted itself, and in the GPU communicates over an encrypted bus from the CPU memory to the GPU using direct memory access. And so we've done that both for CyborgDB, but also to actually run a full LLM in a confidential GPU. It's super interesting, and I think that's going to be the future of it. Anthropic announced in June that they're starting to do work there. I had a conversation with head of product at OpenAI about this, and they're actually interested in it to run it on their customers' environments and protect the model weights themselves. So it's a really interesting space that's tangential to what we're building, but really fascinating.
Sorry to one more thing. This is a personal one. I'm writing a paper, academic paper on it. Can I work with you guys, and are you hiring? This is like proper revolution, because this is like more than what you're explaining. This is crazy good. It's like properly needed, like desperately needed, something we had for a long time. And I think you guys are solving a serious problem here.
Let's chat after this.
Okay.
Good job on asking. You always got to ask, shoot your shot, we call it. Thank you.